What specific problem does the LEAP method aim to solve in the context of large reasoning models, LRMs, and how does this relate to the previously identified limitations of self-correction mechanisms?
The LEAP method aims to address the prefix dominance trap, a specific problem where large reasoning models, LRMs, exhibit a significant performance drop up to 20% when starting from flawed reasoning paths. This issue highlights the limitations of LRM's self-correction mechanisms, which often fail to recover from incorrect reasoning trajectories. By enabling cross-path interaction during parallel inference, LEAP allows LRMs to engage in peer learning, thereby broadening their self-verification capabilities beyond their individual reasoning paths. This collaborative approach facilitates the verification and refinement of reasoning paths, reducing the cognitive burden and enhancing overall reasoning effectiveness. Experimental results demonstrate that LEAP significantly narrows the performance gap caused by poor beginnings, indicating its effectiveness in overcoming the limitations of traditional self-correction methods.
How does the proposed LEAP method work? Please illustrate it step by step, including the roles of the summarization and routing stages.
The proposed LEAP method operates through a structured two-stage process, summarization and routing, facilitating cross-path interaction among reasoning paths during parallel inference. In the summarization stage, each reasoning path condenses its current approach, key insights and intermediate results into a concise summary, limited to 256 tokens. This summary is generated using a prompt that includes a dynamically selected summary trigger and template, ensuring variability while capturing essential information. Following this, the routing stage disseminates these summaries among the reasoning paths. A routing function selects a subset of peer summaries for each path, employing different strategies such as dispersed, clustered, or hybrid routing. Dispersed routing prioritizes diverse insights to break erroneous patterns, while clustered routing focuses on similar reasoning paths to reinforce viable solutions. This interaction allows paths to leverage peer insights, enhancing their self-verification capabilities and improving overall reasoning effectiveness. By enabling this collaborative refinement, LEAP helps models recover from flawed beginnings and reduces the cognitive burden associated with generating new reasoning paths from scratch.
Can you provide a simple example that demonstrates how LEAP interacts with reasoning paths during inference? Walk through the algorithm steps with this example in detail.
To illustrate how LEAP interacts with reasoning paths during inference, consider a scenario where three reasoning paths, Path A, Path B, and Path C, are working on a math problem. Initially, each path generates its own reasoning independently. 1. Summarization stage. After generating a set number of tokens, let's say 4K, each path summarizes its current reasoning into a concise message. For example, Path A might summarize its approach as, "I believe the answer is 10 based on the equation I derived," while Path B might summarize, "I reached 8, but I'm unsure about my calculations." 2. Routing stage. Next, the routing mechanism selects which summaries each path will receive. If using dispersed routing, Path A might receive Path B's summary 8 and Path C's summary 12, while Path B receives Path A's 10 and Path C's 12. This selection is based on the heuristic that diverse insights can help break erroneous reasoning patterns. 3. Peer interaction. After receiving these summaries, each path reflects on the new information. For instance, Path A, upon seeing Path B's result of 8, might reconsider its calculations and realize it miscalculated, leading it to adjust its answer to 9. Path B, influenced by Path A's reasoning, might also revise its approach, concluding that its initial answer was incorrect. 4. Continued reasoning. The paths continue generating tokens, now informed by the peer insights. After another set of tokens, they summarize again, potentially leading to more refined answers. 5. Final output. After several iterations of summarization and peer interaction, the paths converge on a more accurate answer, demonstrating how LEAP enhances self-correction by leveraging the reasoning of peers, ultimately improving the overall performance of the model. This example encapsulates the core steps of LEAP, showcasing how it facilitates collaborative reasoning and enhances the self-verification capabilities of LRMs.
What evidence do you present in the paper to show the theoretical or practical benefits of using the leap method over traditional, independent reasoning?
The paper presents several pieces of evidence demonstrating the benefits of the leap method over traditional, independent reasoning. Firstly, it quantifies the prefix dominance trap, showing that LRMs experience a nearly 20% performance drop when starting from flawed prefixes, highlighting the limitations of self-correction in traditional models. In contrast, models utilizing leap significantly reduce this performance gap, with DeepSeek Distill Quen 14b narrowing the gap from 1988 to 781, indicating improved self-verification through peer interaction. Additionally, comprehensive evaluations across multiple benchmarks, including AMY 2024 and GPQA Diamond, reveal that all reasoning models with leap outperform their independent reasoning counterparts, with DeepSeek R1 Distill Quen 7b exceeding the baseline by 6.49 points on average. Furthermore, human verification studies show that the proportion of correct responses increases from 25% to 62.5% when using leap, demonstrating its effectiveness in correcting flawed reasoning paths. Overall, these findings underscore the practical advantages of leap in enhancing reasoning accuracy and robustness compared to traditional methods.
Describe the experimental setup used to validate the leap method. What benchmarks and metrics were utilized to assess its performance, and how do these support your claims?
To validate the leap method, we conducted experiments using competition-level mathematics datasets, specifically AMY 2024, AMY 2025, and the AIMO 2025 reference set, which contain a total of 70 problems. We also included the GPQA Diamond subset, which consists of 198 challenging questions requiring advanced domain knowledge. The performance of the models was assessed using two primary metrics: PASSET-1, which measures the correctness of the top response generated, and CONSA-10, which evaluates the consensus among multiple responses generated for each question. For the experiments, we generated 32 responses per question using a non-zero temperature to encourage diversity, and we compared the performance of models with leap against baselines using independent reasoning. The results showed that models utilizing leap significantly outperformed the baselines across all benchmarks, with improvements in PASSET-1 scores and consensus metrics, thereby supporting our claims about the effectiveness of peer learning in enhancing reasoning capabilities in LRMs.
What limitations or potential drawbacks did you identify in the leap method, particularly regarding its implementation and performance under varying conditions?
The leap method, while effective in improving reasoning performance, exhibits certain limitations and potential drawbacks. Firstly, smaller models, such as DeepSeek R1 Distill Quen 7b, sometimes struggle to effectively summarize and reflect on peer insights, indicating a need for further training adaptation to enhance their performance. Additionally, the communication granularity and traffic can impact performance. Increasing the frequency of communication, smaller t, slightly improves accuracy but at the cost of higher token usage, suggesting a trade-off between efficiency and effectiveness. Furthermore, while leap demonstrates robustness against incorrect paths, its performance can still be influenced by the proportion of correct beginnings, as excessive noise from incorrect paths may overwhelm the reasoning process. Lastly, the analysis indicates that communication is most beneficial in the early stages of reasoning, with diminishing returns as reasoning progresses, which may limit its effectiveness in more complex problem-solving scenarios.